All right, so I wanted to take a moment and go over what we talked about the last couple days in class. Primarily, this is basically Chapter 7, Section 1. I know you guys did your reading notes quiz over this material already, but it's sometimes nice to have a place where you can come back and just have it all condensed where you need it to be. So, the main ideas behind Kepler's laws and his observations, obviously, we talked about this in class, it all came from the mountain of data and evidence that Tycho Brahe and Copernicus and Galileo had begun accumulating. He basically sifted through all of that data and found these three primary observations. And there's a lot of details and nuances and additional stuff that shows up with these. But these are the three big ideas. These were his summary of those ideas, and we'll talk about some of the details there too. But the first law, because remember, scientific laws are just observations that follow a mathematical pattern that we can use to predict stuff. So the first law that Kepler found or figured out was that things don't actually travel in circular orbits for the most part, right? Only the really, 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 really large things like Jupiter is really close to having a nearly perfectly circular orbit, but even that one's not circular. Comets, usually the smaller you get, the less circular they become, the more elliptical. That's the shape of the orbit, right? It is an ellipse. And ellipses are different than circles. Circles have one center point, and the distance from that center to all of the edges stay the same. Ellipses don't. The more oblong or elongated that circle becomes, the more oval shaped that circle becomes, you wind up with two different centers. Instead of having one center at the very middle of the object, you wind up with having two of them. And we're not going to get into the geometry or structure of an ellipse and why there are those two. But when we say that the sun is at one focus, the sun is literally sitting at one of those two central points that come out of taking a circle and basically stretching it, squishing it, however you want to describe it. The other focus, the other center, it doesn't have anything. It's empty space. There's nothing there. But what this does mean, right? This was Kepler's first law. That was your answer. Sorry, to letter C. It was his first law. What that does mean is that your distance from the sun changes, which is really weird to think about, but it does. So the distance from the sun here, let's call this the month of December, because that's pretty much, obviously not to scale, but it's pretty much where we're at right now. In the month of December, because it's elliptical, the distance that you are from the sun, and remember we measure all of our astronomical distances from the center of the objects, right? Not from where the object begins and your object also begins, or the front or the back, or left or right. These are spheres, and so we always measure them from the center. And these radii, the two radiuses that are depicted here, are different lengths because this isn't a perfect circle. And that has a whole lot of implications when we go back to talking about Newton's laws, especially F equals ma, and we talk about the force of gravity and how it can change based on how far away you are from the source of gravity, and all sorts of stuff I'm going to get into here towards the end of the video. But the main idea is that these paths are not circular, they're elliptical, and your distance from the sun will change. It will fluctuate from week to week, month to month. Right now in December, we're closer to the sun than we will be for pretty much the rest of the year. December, don't quote me on this, I know I'm putting it up online. December 22nd, whatever that winter solstice is, I believe is our closest point, so we're approaching that. And then gradually for the rest of the year until we hit, May, June, July, we'll be getting further away from the sun. And we'll reach our furthest point all the way out there, and then we turn around and we come back. These distances aren't very large. They aren't enough to, cause temperature changes, right? The seasons actually come from the axial tilt of the planet and whether or not we're facing the sun or pointed away from the sun, ironically enough. Clearly, it's December. We're closest to the sun than we will be for the rest of the year, and it's the coldest it will probably be for the rest of the year. So it follows, seasons follow the axial tilt. We're talking a couple 100,000 miles maybe It's not that much of a difference, but it is not a perfect circle. We do move forward and back. Now, we're going to step away from looking at one planet's orbital path, and we're going to compare all of the different planets that we've got. And this is one of the things that Kepler was probably most well known for, is his ability to sift through all of this data and make sense of all of it. Just by observation, we found that the mean orbital period, basically the amount of time it takes Mercury to make one trip around the sun, was around 88 days, and Jupiter winds up being around 12 years. So how did he explain the differences between those two periods, between those two planets? It all came down to Jupiter, as we saw in the video today and yesterday, has a larger radius. Jupiter is a larger radius, and the further away you are from the sun, the longer it takes to make one trip. That's the idea. Or at least that was his first, maybe prediction, estimate, guess as to why all of this worked. Then he sat down and he actually started crunching the numbers. And to calculate linear speed, centripetal acceleration, this is stuff that we would have done in Unit 6 previously. Obviously, we had to gloss over a lot of that. That's putting it politely. But to calculate linear speed, it's still just a velocity. So we're going to calculate velocity the same way we would have always calculated velocity. It's distance divided by time. The catch here is that we're not going in a straight line. So if you want to find the distance around a circle, you actually have to use 2 pi r, because that's your equation for circumference, and divide it by the amount of time it takes to make a circle, the period. And this is where we're able to get our linear speed, our tangential velocities, orbital velocity, whatever one of those synonymous terms you'd like to use to describe it is entirely up to you. Now, again, I'm not going to make you memorize any of these values for any of the planets, and I will emphasize that until I'm blue in the face. The textbook has all of the numbers that you're going to need. I use the numbers from the textbook for all of the problems that I choose. The issues with finding them online might be the answers, or the numbers that are given online might be rounded, they might be estimates, slightly different estimate because different places measure things with varying degrees of precision, which is really all it comes down to. And then there might be, when you're talking about things that are really, really, really far away and you're off by, 1% of a lot of money is still a lot of money. So, 1% of Jeff Bezos' net worth is not the same as 1% of my net worth. So, those are two very different things. So in this particular case, use the values from the textbook. On most of the worksheets I gave them to you. When in doubt, ask. If you find them online, they might have the wrong units, or they might be, less precise measurements, whatever. I use the textbook because that's what the school provided me. Anyways, so the idea for this is to take the radius, orbital radius of Mercury, which we can get from the book, and plug it in here, divide it by that, there's the value from the book, divide it by that 88 days, and you should get an orbital velocity of 47,868. 868 meters per second. That's pretty quick, right? The centripetal acceleration or orbital acceleration, because acceleration is usually how your speed changes, right? That's what we've described it so far as. It's whether or not you're speeding up or whether or not you're slowing down. Well, in this case, we're turning. The planets are making circles. So the equation for centripetal acceleration had to change a little bit to account for the fact that you're now pointed in a different direction. And we did that by taking your tangential velocity and squaring it and dividing it by your radius. Now, in that unit, I would have explained why this is the case. So that was something. Sorry, I had to pause real quick. That was something that we would have discussed a lot more in detail back then. It's not that big a deal. In this particular case, your units still work out to be meters per second squared, and we are, from that going to be able to use this information. But I'm not going to ask you to calculate centripetal accelerations or orbital accelerations. We're going to stick to the 5 equations that are on the front of the unit packet. Anyways, the acceleration that Kepler would have found or others, even still to this day, this was actually what your first lab was supposed to be, would get you that particular value for centripetal acceleration. It's not a lot, right? It's really, 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 really small value for centripetal acceleration because planets are massive and they're really far away. They're not turning very quickly. It seems really quick for Mercury, at least, compared to Jupiter or something. But those are the equations we would have used. You're not going to have to use them in the future. We're not going to come back to this. But that's where I got those values. If you want to plug stuff in, play around with it, double check that I'm not lying to you, go for it, happily. I'll let you do so. And if you spot a mistake, extra points, extra credit. But we've got linear speed for Jupiter is what they wanted us to calculate. And I'm going to use the exact same values. Now, you got to make sure that you convert your units of time into seconds. That's probably the part that people hate the most. But when you do so, you'll get a linear speed for Jupiter of around 13,079. I think it was like 79.9, so 13,080. And a centripetal acceleration of 0.030, 0.22. So significantly slower or dramatically less orbital acceleration because it is so far away. Now, Kepler was just collecting this data, making these calculations, and trying to come up with these observations. So he did come up with a couple of things that are totally going to be what I expect you to be able to do, right? B and C, not much. D and E, yeah, absolutely. Orbital velocity, the closer you are to a star, the faster you're going to be moving, right? That's definitely a trend that we observe. In the video that we watched today, still linked on Teams, is a fantastic visual of all of that. Sorry for the Teams thing going off. And acceleration, the further away you get, you're going to have less acceleration. Now, you're going to get less acceleration because of something we've actually already talked about. If we've got the sun all the way over here, and I'm going to put the Earth over here and the planet Jupiter all the way over here, right? So if we've got the Earth and Jupiter orbiting the sun at different distances, right? We saw in that video Jupiter is significantly further away from the sun than the Earth is. Why is there less acceleration? And this is where Newton kind of came back and stepped in and helped Kepler out, maybe not directly, but helped out, the other scientists with these calculations, was when he derived this guy, F equals GMM over R squared. It turns out the further away you are, Jupiter has a significantly larger radius than the Earth does. The further away you are, the weaker that force of gravity on you is going to be. And the key here is to remember that the force of gravity is the only thing keeping the Earth in orbit. It's kind of like, and this is the example I used in class, spinning your keys around in a circle on your lanyard, right? You've got to constantly be applying that force to keep it moving in a circle with your fingers, with your wrist, with your arm. And the moment you let go of that, the keys don't naturally continue moving in a circle. Things don't naturally tend to follow circular paths. Inertia, what we talked about in our last unit, is the tendency for an object to keep moving at its speed and in that direction forever unless acted upon by an outside force. That was Newton's first law. And so the sun is continually applying this force, but the further away you get from the sun, the weaker that force becomes. Notice the length of the arrows. That's how we draw our vectors. And the length of the arrow is proportional to how strong that force is, or the magnitude of that number. And the force of gravity on Jupiter is significantly less than it is on the Earth. And this is why there's less acceleration, because you can take that idea and then come back to F equals ma. You're going to have less force, less acceleration. More force, more acceleration. And that's why these planets move at different speeds around the sun. It's all got to do with the radius. The closer you are, the more gravitational force the sun exerts on you, the quicker you're going to be accelerating, the faster your speed is going to be around that star. The further away you are, the opposite is true. And that was the main idea there. Now, the implication of that, obviously, this was a comparison between other planets, but then let's go back and connect it to the fact that planets themselves don't follow circular paths, right? Planets themselves have different radiuses based on where they're at in their year, in their trip around their star. The closer you are, still, the faster you're going to be moving. The further away you are, still, the slower you're going to be moving. That's a main idea for this entire unit. The closer a planet is, or any object is, to the thing it's orbiting, the faster it's going to be moving. And this actually is a really good example of why things wind up coming back. Think of like throwing a ball up in the air. If you throw a ball up in the air, like we've done a couple of times, it will gradually lose speed as it goes up into the air until it finally runs out of that vertical velocity that we gave it. It turns around and it comes back. And that's exactly what these planets are doing. It's the same basic concept. It's just they're moving significantly faster than, you were able to throw a ball up in the air for that lab we did a few months ago. Kepler's second law, his second big observation, stems off of all of this. And we're not going to do any math with this one because it deals with, in algebra or geometry, I'm sure you guys did some arc length measurements in order to find out how many arc seconds pass or how far the arch might be right here on a circle. Well, ellipses, it's the same idea, but it's significantly more complicated because the radius changes and you don't have that consistent value there. So we're not going to do that. But the idea that he found, and I'm going to simplify what the book gave you guys here, is equal area in equal time. And what that means is that even though the area swept out in section B looks like it should be a lot greater than the area swept out in section A, if the transition from where B starts to where B ends represents 42 days, then the transition from where A begins and A ends is also going to be 42 days, right? The longer radius basically makes this a more narrow piece or of area, but it overall the area winds up still being the same. So equal area, equal days. If the transition through area B took 42 days, then the transition of 42 days on the other side of this planet's orbit would also give you the exact same area. That's applicable in a lot more complicated astronomy stuff, so we're just going to stick with equal area, equal time, and then the main idea here with number 3 is primarily what I'm going to be asking about for Kepler's second law. Kepler's third law is the one I've gotten a lot of questions about so far today, which is why I'm rushing this video and trying to get it out to you guys. And Kepler's third law is the proportional relationship between different kinds of objects. If two objects, and this is where this equation comes from, what he noticed is, and his two objects were always like something orbiting the sun. So it was the Earth orbiting the sun or Mars orbiting the sun when he was making his observations, but we have found it to be true for everything. So if we're looking at, in this example, the moon orbiting the Earth, it's going to do so at a certain distance, and it will take a certain amount of time to make one trip around the Earth. We call that its orbital period. That's going to be the same for any object at that distance away from the Earth. So because the mass of the thing doing the orbiting and all this stuff I talked about in our last video cancels out, we can take, and that's what we're doing here, our information that we know about the moon, its orbital radius and its orbital period, and we can compare it to the information of a satellite that is also orbiting the Earth. They're proportional in that regard. And that was his third big observation. So because they're proportional, the equation that he came up with, again, not going to sit down and go through all of the data that he did to derive this for you again, but he found that the square of the ratio of the periods of the two objects was equal to the cube of the ratio of the distances that those objects were away from the thing that they're orbiting. And so this is the equation. This is straight from the cover page of your unit packet, right? I think this was the fourth equation that was there. So like I said in class, the hardest part about this particular problem is just identifying what you want to be object A or object B, and then making sure you plug the values in the correct spot. So organize these lists, always make a list, right, of the two objects that are orbiting the Earth. In this case, we have the moon and our artificial satellite. The radius that the moon is going to have the distance it is from the center of the planet Earth is 384 million meters. So instead of writing 384 million meters, I'm going to use scientific notation because I don't hate myself. And then the period was 27.3 days, which is why you get one full moon a month, right? 27 days is about a month. So that's our information about the moon as it orbits the Earth. The information given to us about the satellite as it orbits the Earth is a period of 9.1 days. So it's going to be a lot closer because its orbital period is a lot lower, just like we watched with Mercury and Jupiter on the last page of this. And the orbital radius is what they asked us to solve for in this particular problem. Here's my trick for solving any of these. Your unknown, to make the math easier on you, always make your unknown object A, and the thing you have all of your information about, object B. Because you don't want your unknown, your variable you're solving for, to be in the denominator. We can solve it that way. I did that in class. It's a lot longer because you got to get that variable out of the denominator in order to get the correct value. And it's an extra step that we really don't need to undergo if we just make our unknown object A. So let's go ahead, plug our stuff in here real quick, and wrap this all up. We've got a period for the satellite, which is 9.1. 27.3 days was our period for the moon, and so I'm putting A and B in there respectively. And then the radiuses, our unknown radius for the satellite goes up in our numerator. Again, notice both numerators have our information about the satellite, and both denominators are going to have our information about the moon. And then this one was 3.84 times 10 to the 8th meters. We're going to cube that as well. When you go to solve these and plug everything in, I think it's a lot easier just to simplify what you've got. And take the entire left side right here, simplify that, right? 9.1 squared divided by 27.3 squared, reduce that down to one value, and then multiply. That'll be your next step. So this is step number 1. Simplify that. Step number 2 would be to multiply both sides by 3.84 times 10 to the 8th power, cubed. So multiply both sides by that to get it out of the denominator, and then don't forget at the end of all things to not square root, but cube root. So that was step 1, step 2, and step 3 for how you solve these. At the end of all of it, you should get the exact same values that we had in class. There were a couple of other really good questions about number 8 is usually a pretty popular one. There's nothing fancy going on with number 8 other than, I suppose, the introduction of a new unit that you might not be familiar with. The distance between the Earth and the Sun, yes, it is 93 million miles. Yes, it is about 150 million meters, but those are really large numbers, and I don't like writing those, and I guess a lot of astronomers also didn't like writing those. So the information that you've got for number 8, just to kind of help get the ball rolling on that one, you can use this value of 1 AU, 1 astronomical unit, as your distance, right? It is 93 million miles and 150 million meters, just like 12 inches is a foot. It's just another unit that we can use. And from there, you should be able to figure out, the other pieces of information that you need. You've got the period of the, the period of the Earth around the Sun is 365. If you want to be annoying and nitpicky, you could make it 365.25 to account for that leap year thing, but I really don't care about it. The period of Mars around the Sun is 686. They're both measured in days, so you don't have to worry about that. The radius of the Earth around the Sun is 1 astronomical unit, and the radius around Mars is what you're solving for. It will probably come out to be measured in AUs. You could, I don't have the answer at the bottom of the page reported in meters or in miles or in kilometers. My answer at the bottom, as you can see, is clearly reported in astronomical units. I think it's easier. But that's the only thing that changed with number 8. So I hope that helped. Let me know. Obviously, if you've got questions, concerns, anything like that, I'd be more than happy to walk you guys through anything else.